Hi, welcome back. How are you guys doing? I'm Naomi Lowe, as you know by now, and we will be talking today about making sense of significance. This is lecture 6. And as you know, significance doesn't mean importance. Get rid of that connection for this class. It means that you rejected the null, or that you decided that there's little chance your sample statistics, your sample results, occurred because of chance. And it's more likely that they occurred because of a difference from that null, because your null is false. Okay. So today we're going to talk about errors in statistics, because we are dealing with a population and we'll never know all the scores from the population. All we know is our sample, and we make a decision based on how the probability of getting that sample from this theoretical null population. We never know if we're 100% accurate or not. There's still room for error. We could be right, we could be wrong. We try to limit that error, but there is error. We'll talk about 2 different types of error, type 1 error and type 2 error. Then we'll talk about importance, or how drastic the effects are of what you're looking at, which we call effect size, which is different than significance, effect size. And then we'll look at power, different types of power, your ability to detect a difference between groups. And we'll look at both a priori and retrospective power. All right, so we have 2 types of error. Type 1 error is rejecting a null when it's true. Okay. So the null being true, if you think about the null as both groups are equal, no difference. Okay. Just think of it as no difference. It's a two-tailed hypothesis, but let's think of it as no difference. That means that the null's true. There really is no difference. They're equal, the groups. And you reject the null, so you could decide the groups are different, but you're wrong. You made an error. Now, we don't know whether we made the error or not, but if you made a decision to reject the null and you made a wrong decision, you got out in that tail just because of sampling error, it's possible, then you'd be making a type 1 error. A type 2 error is when you do not reject the null, so you retain the null, you keep the null, you decide, you're not going with your alternative hypothesis, you keep the null, but the null's false, indeed, and you should have rejected the null. The groups are different. Playing video games really improves your score, but you didn't decide to reject the null, you retained it, you made a type 2 error. All right, so here we have a table, and I'm going to go to my drawing over here with this table, where I give you an idea of how we make these 2 different types of errors. The reason we have these 2 different types of errors is because you can have 2 different decisions. Okay? You have one decision. You can either decide about the null that the null is true and you retain it, or you decide that the null is false and you reject it. Those are the only 2 statistical decisions you make when you're doing hypothesis testing. You decide retain the null or reject the null. Okay? It's only 2 decisions you make. Now, here's the truth over on this side. Now, the truth is what we don't know, okay? But it exists. Either in reality, in truth, the null is true, or the null is false. So either the groups are the same or they're different in reality. Okay? We'll never know this, but we make a guess up here. Now, if we guess based on our sample, not just any guess, but we use probability, statistics, and we make the decision the null's true. We retain the null, too bad. We have nothing to support our alternative hypothesis. This is our decision, is true. Okay? Now, we have 2 options under this decision. Either in reality the null is true, or in reality the null is false. Now, if you make the decision that it's true, and in reality the null is true, you didn't make an error. This is good. Put a little happy face there. Ha! That's exactly what you want to make the correct decision. But if you decided that the null was true and you made an error where the null was false, okay, that's not correct, and you decide the null's true. So by deciding the null's true, that means you're within this retain region where you decide that your sample stat is no different than this comparison distribution. So you keep within this null, you decide it's true, and indeed the null is false. The group you're comparing doesn't have a mean that's equal to your comparison distribution. The mean's out here somewhere. So that's an error. This is a type 2 error. Okay. The other decision you can make is that the null is false. You only make that decision if your sample stat falls out here in the tails. It's not likely to happen if the null is true, but it could. If you're sampling from a population that is equal, that means equal to this comparison distribution. That means that the null would be true, that they're equal. you could get a sample stat out here in the tail. It's just not very likely. So suppose you get a sample stat out in this tail beyond your rejection region, okay, and you think, okay, it was way out here. You think that your second population you're comparing is out here, not in here, like your null hypothesis, and you reject the null. You decide the null is false. The groups are not equal. Now you could be correct. Okay? That null could be false and it's out here. If you're correct, the null is actually truly false. Good job, smiley face. Hooray, you get to celebrate. But suppose that the null was true. Both groups were equal, and you just got a score way out here by sampling error. Remember, it happens. Remember shuffling cards? You might get an average of 1.5 that goes way into that tail just by chance, just by the luck of the sample you drew. Not likely, but it can happen. If that happens and you reject the null based on that sample, where the null is really true, the groups are equal, then you made an error. This is a type 1 error. When you end up in this rejection area, you reject the null, you decide that your alternative hypothesis, your research hypothesis has an effect, when indeed it doesn't have an effect. So let's look at these two different scenarios. You reject means your alternative, your research hypothesis, whatever you're interested in, whether you're testing whether a drug works, that would be deciding to reject the null, it works. Deciding to retain the null, nope, doesn't work. Both groups are the same whether they take the drug or not. Now, those decisions, if you make a decision that the null is true, the groups are equal, you're saying either really they're equal, happy face, which isn't so good because the drug doesn't work in that case. You're saying, at least you made the correct decision about the drug. You say, nope, groups aren't different depending on the drug they take, but you made the right decision. You're not going to spend money on a drug that doesn't work. Or you could have made a mistake. You just didn't have a strong enough study to find that that drug worked. Okay? You had too much standard error. Remember, the smaller your sample, the more standard error you have. You might make this type 2 error. This is another type of situation you want to think about. If you decide the null's false, you reject the null, that means you decide that the groups are different. The group with the drug maybe improved, and either you're correct, the group's really improved, the null is false, and smiley face, good, market the drug. Otherwise, if you're wrong, making a type 1 error, that means you ended up out here in those tails by chance, and you really should not be rejecting the null. The drug doesn't work. That was just random sampling error. Bad thing. Okay? So you don't want to make it. That's why they limit this type 1 error. Type 1 error is the same as alpha. Type 1 error is set. Because it's in the tails, it's the percentage of times you'll end up in those tails just by chance if the null was true. If this is your null comparison distribution, and if it was true, if you just calculate the area under those tails, it gives you the probability that you'll get a sample stat in that area. So you set the limits. You set the 5% at the end. And then alpha, if it's at 5%, you have a 5% chance of type 1 error. Okay? Type 2 comes a little differently. Type 2 error. All right. So now that we've talked about error a little bit, let's look at effect size. I told you that significance doesn't tell you how big of an impact the treatment had. Just because you say something was significant, if I say video games significantly change your score on a math exam, that doesn't mean it changed it 0.5% or 20%. It just means that it was not likely that the change in the score was only due to chance. It was likely that change in score happened because of playing video games or not. So effect size calculates how drastic an effect actually is. And this is this example I have is just a simple calculation of differences between two means. Okay? This is typically called Cohen's d. Cohen's d is just taking mean 1 minus mean 2 divided by standard deviation. So essentially it's telling you the difference between the two means in terms of standard deviations, how many standard deviations apart those two means are. And this is great because it doesn't matter whether you have a test that has 100 points or a test that has 5 points. You can look at the difference in terms of standard deviations. It's almost like a standardized score for that difference, a standardized effect size. The bigger that Cohen's d, the larger the impact or the effect, the larger the difference between the means. The smaller the Cohen's d, the smaller the effect. And here are some different criteria for Cohen's d that are widely accepted. If Cohen's d is 0.2, it's a small effect. If it's 0.5 or above, it's a medium effect. And if it's 0.8 or any larger than 0.8, then it is a large effect. Okay, so let's go back to the drawing board. Here I have an example of Cohen's d. Remember the example I gave last week's lecture? My son, he'll be happy to know that his science project has gone a long way. But he was comparing two groups, one that played video games, one that didn't play video games. The population of 2 was known with a mean of 70, standard deviation of 2. Mean 1, we were testing the kids who played video games. We wanted to know if it was different, their math scores different than the ones who didn't play games. So remember I gave you an example. He had 10 students take the test and the mean was 67. Let's calculate the effect size for that. All you do, according to Cohen's d, you take the mean 1, 61, minus mean 2, 70, divide by the standard deviation 2. So go ahead and calculate that. So we have 61 minus 70, negative 9, divided by 2. And it says negative 4.5. Oh, sorry, 61. Made a mistake. Glad you're paying attention. You caught me there. Let me know if I make any others. So wrong calculations. 67 minus 70. 67 minus 70. We'll get it one of these times. Equals negative 3. Divide by the standard deviation. Equals 1.5. So Cohen's d here is 1.5. It's negative. Now, this scale goes the opposite too. The negatives are large. So if you just take the absolute value of this Cohen's d, that tells you, instead of negative 1.5, it tells you it's a large effect, but the population 1 was below population 2. Just take the absolute value of that, 1.5, and you see it's a very large effect size. It's above 0.8. So this is a large effect, but it's an effect in the wrong direction. This isn't the real data that my son got. If he had gotten this, he probably would have been devastated. He would have hidden the data from me so that I wouldn't see this and tell him he couldn't play video games anymore. So this is a large effect, not so great. My son said, or not so great for him. My son said, suppose he did this and he goes, oh, that was awful. I'm going to do the study again, but I'm going to have a sample size of 30 because this bigger sample size is better. So he goes out and does the same thing with 30 people. And his new mean of those kids who played video games for 2 hours was 71. Let's calculate the effect size for that. All you do is 71, mean 1 minus mean 2, 70, divided by 2 equals, go ahead, let's see if we can get the calculator working this time. 71 minus 70 is 1, divided by 2 equals 0.5. So 0.5, and if you look at our effect size, that's a medium effect. So it's a medium effect above the population 1. It means video games had a medium effect, but this time it increased their scores on this math test. So I'd wonder what he was up to when he did the second thing, since his results were so different here. So that's simple, the way you calculate effect size. All right, now that we've calculated effect size, let's look at power. Power is your ability to detect or to reject a false null. Okay, so think about this. A false null. A false null means that there is a difference between the groups, that the population, so in my son's case, it means that the kids who played video games did score. If you had all kids playing video games, they would score differently on a math test than all kids not playing video games. Okay? It means that in the population, the null is false. The two groups being equal is false. But your ability to detect that statistically and reject the null depends on several things. Let's look at an example here. So if you have the comparison distribution, remember we have the comparison distribution. This is population 2 with a mean of 70 on this exam and a standard deviation of 2 or a standard error of 0.5. So we're using means, we're comparing means, so you want to use the standard error, not the standard deviation of 0.5. Now, so 70.5, which is pretty small. Remember that was with an n of 16. The standard deviation of those all possible means was 0.5. The standard error was 0.5. So now in order to figure out our ability to detect or reject a false null, that means that this population 2 is not equal to population 1 in reality, but we don't know this. Okay? So population 1, kids who play video games, let's say they scored higher. In reality, the population, the average of those kids is higher than 70. Okay? Now, so let's say that the average, I'm going to move this over, hopefully you got the rest of that by now. So let's say that for population 1, their score, the average is right here. Okay? This is the average. We'll say it's 76, okay, of population 1, kids who play video games. Now, depending on the size of your sample, here at 16, you're going to have a 0.5 standard error or spread of all possible sample means. You might get a sample mean here, you might get one here, you might get one here. The only time you're going to reject the null is when you go past that 1.96 cutoff, remember that we did before, into this rejection region. So the way that you are going to calculate power, power is going to be determined by how far your sampling distribution is spread out, which is determined by your sample size. So n is very important, your sample size is very important in this spread. If you have a really large sample, really large sample, then all possible sample means would be really close to that true population mean for population 1. They'd be centered around that. So let's look at, back at our lecture, let's look at steps for figuring out power. First, you want to gather the information needed. You want to get the mean and the standard deviation of population 2. And that's because you need so first you do population 2. You need the mean and standard deviation of population 2 and the predicted mean of population 1. Now, if your power is your ability to reject the null, that's going, okay, if I do a study where the null's false, where the groups are different, am I going to statistically be able to reject the null? And what percent of the time, because remember, you might get a sample that's extreme in the tail and it doesn't get rejected. So what percent of the time am I going to reject the null? That's your power. So then you need to figure the raw score for the cutoff point on the comparison distribution or population 2. And then the next step, you figure out a z-score. So let's actually go back to those first 2 steps. And I'm going to show you on my drawing what we do with step 1 and step 2. So here's population 1 on my population 2, kids who don't play video games, and this is centered around 70. In the middle, you determine your cutoff score where you'll reject the null. And this is your cutoff region, 1.96. So that's your z-score there. And that's your cutoff region, or I think it was 1.64 if we were doing a one-tailed test. So let's get this up here. 1.64 for a one-tailed test. For a two-tailed test, it would be 1.96. So let's do one-tailed 1.64. Here you have 5% in here, but you're assuming power relates to when the null is false. So if the null is false, that means your population 1 is not centered at the same point. Otherwise, the null would be true. If population 1, kids who play video games, is centered around that same point, has the same average, but that's false. With power, we're determining how can we detect that is false, if it is false. So first you have to estimate what is the mean of population 1. What's the estimate? And typically you get this, so you need to know the effect size. What are the difference between the means of population in 1 and 2? So you need an estimate of effect size, which typically is done from similar research in the past. Sometimes it's estimated small, medium, and large effect. But say you decide that from past research that it's probably going to be a mean of, 76. And so you place that there, 76. This is your population 1 estimate. And then you take the z-score, the Z cutoff score, and you change it to a raw score. Change it to a raw score. So you say you converted this back to a raw score, and this was 74 was the raw score. So raw 74, I'm not calculating it, but raw score 74 was equivalent to the Z cutoff of 1.64. Then you take that raw score up to this distribution, and you look at, based on a specific sample size, if you had a small sample, you're going to have a small spread. If you had a larger sample, you're going to have a larger spread. But you look at what percent of the time with that size sample, and you know the spread because of standard error, you calculate it based on the predicted mean, and your predicted use of the sample size, you find out here, so this is probably a distribution with a small sample, maybe a sample of 5 or 10. You look at this and you can find out the area under here, and that's the time that you would reject the null because you went past that cutoff. And so this is the percent of the time that you would reject the null when the null is false. That's your power. Here you can see with a larger sample and less spread for this, the distribution of sample means, this percent of this curve is a lot more than the percent we had before of the curve. Where if you had a really wide sample or a really small sample, you have less of the percent of this curve under here. Hopefully that's making sense. Okay, so the next 2 steps for calculating power, I kind of went over them, but here they are for your notes. You need to figure out the z-score from this cutoff point on the distribution of mean 1. So you found the raw score, you transferred it up to the population 1 sample distribution that's predicted, and then you need to convert that to a z-score, but not using population 2 information anymore, now using the predicted population 1 information. Change it to a z-score, look up the area to the right of that. If you're doing a right one-tailed test, if you're doing left, you go the opposite direction. Find the area under that curve, and that's your power. That gives you the percentage or the number of times out of 100 that you would reject the null if that was the true difference between your means, the predicted difference. Now the problem with this is that a lot of times we don't know the difference between our means until after we've already collected data. So there are several things that affect power. One, sample size. As sample size goes up, power goes up. Because as sample size goes up, what happens to standard deviation of the means or standard error? Sample size goes up, you divide by sample size, if that gets bigger, standard error shrinks, and it allows us to reject the null more if the null is false. Significance level, alpha, also affects power, because if you have a 5% cutoff, that gives you more region to reject the null. You're going to reject the null more often. It increases power. But it also, if you're increasing power, you're rejecting more, you're also increasing type 1 error. Remember, alpha level of 0.05 or 5% has a 5% type 1 error. Smaller alpha, 1%, has a 1% type 1 error level. That's the number of times you would make a type 1 error if you did this over and over and over, the probability that you're making a type 1 error. So even though if you 5%, if you increased it to 10%, your power goes up. You're also increasing type 1 error, falsely rejecting a null that shouldn't be rejected. So another thing that affects power is a one-tailed versus two-tailed test. How much area there is, you're dividing the alpha by the 2 tails, and the procedure. Depending on how you do your experimental treatment, sometimes you can make a big impact, so you make the means really different from each other, and it makes power higher. It's easier to reject a false null when the mean difference is really big and your sampling distribution centers around this number way over here, compared to means that are really close together. You're going to have a hard time rejecting the null, because even if there's a difference, a small difference, you're going to have a hard time, if there's overlap between your 2 populations. So this is a table that just summarizes some of the things that go into power. We've talked about most of them. If you have a large effect size, it increases power. Large effects means bigger difference between your means. Smaller effect size decreases power. If there are large differences between the means, increases power, same thing. And a small standard deviation increases power. And that's because, I'll just draw, so while you can see this, I'll draw you a little picture. If you have a small standard deviation, that means population 1 is going to be like this, and population 2 is like this, and population 1 is like this. So there's not a whole lot of overlap. Most of the time, you're going to reject the null. All this time, you're going to reject the null. Where if you have a large standard deviation in your population, then this rejection region, if you move it up here, you're going to reject fewer amount of the time, or a smaller amount of the time, than you would before with this smaller standard deviation. So standard deviation, remember standard error equals standard deviation divided by the square root of n. So the standard deviation, as that gets bigger, it's going to decrease your power. As it gets smaller, it also makes standard error smaller, and it increases your power. All right, back to the table. A larger sample size increases power, and a smaller sample size decreases power. And we already talked about the others, one-tail versus two-tail, your significance level. Those are things you should think about when you're addressing power. Now, there are two ways that power can be used. One of them is a priori, where you ask yourself, okay, what power do I want? And you, based on an effect size you plan to get, you determine what sample size is needed to have a good power. So a power over 0.8, power over 0.8 or 0.9, depending on how good you want that power to be. You have to decide what level are you willing to work with, because if you don't have a powerful study, if you have too small of a sample size and your power isn't very high, then even if the null's false, you're not going to be able to reject it. If your power's at 20% and you go and do the study and there's an effect there that exists, but you don't have a big enough sample to find that effect, why even do the study? Because you're never going to reject the null, whether it's true or not. So this is a really good way to use power, is a priori, going into the study, planning how big of a sample should I use. But probably the most commonly used power is retrospective power. Not such a great way to use power. Retrospective power is after the fact, after you've already collected a sample and you've analyzed the data, you take the difference between your two means, your sample means, and you then base your effect size on that difference in your sample means, and then you decide, okay, with the sample size you already used, you can't change that, what was power? And you calculate power, because there's three things that go into it. You have sample size, you have sample size, effect size, and power. So you can take any one of those out of the equation. You could take out power and calculate your power. Or if you have the power you want, then you can calculate the sample size you need at a certain effect size. So retrospect calculates power, that's the one missing component, after the fact, using the sample means to estimate effect size. The problem with this is if you don't reject the null, okay? If you have NS results, non-significant results, and that means that your decision was that the null is true, or both groups are identical, equal. The tiny little difference you saw, if you did not reject the null, you retained the null, you decided it was only due to error or sampling, random sampling chance, and not due to true differences in the population. So if that's the case, and you're basing that tiny difference, if you're basing effect size on that tiny difference, you're going to say effect is really, really small, and you're going to go, oh, my power was really low, because to detect such a small effect, I would have needed a huge sample size. When you already made the decision to say that that difference only reflected sampling error. So that doesn't make sense at all. A lot of times it's used as an excuse by authors in literature. They'll say, oh, I didn't reject the null, but my power was really low based on these sample mean differences. So maybe I need to go and collect a larger sample, and it gives them an excuse to do more research. It'd be better if they had some solid evidence on the effect size beforehand and planned a priori power. All right, so that's all for today. We covered effect sizes, we covered power. Hopefully you're getting these concepts. I suggest going through, practicing with them. Let me know if you want me to clarify anything. I'd be more than happy to do that. And I will see you all soon.